Hello, in this video we are going to look at the golden ratio and all of its magical properties. So the golden ratio, which we'll cover very soon exactly what it is, and we'll prove it as well, has fascinated some of the most influential people throughout history. So it's fascinated Plato, it has fascinated Euclid of Alexandria, the man who wrote Euclid's Elements, or just Elements I guess, because they're already his elements, Pythagoras, Leonardo da Vinci. This is not a comprehensive list by any means. This is just a very short list. It's influenced them in many ways. They've used it immensely, as we will cover very soon. So the golden ratio is a number. If you were to write it out, it looks something like 1.61803398875, and there's more decimal numbers as well. None of these numbers repeat, or they don't repeat in a sequence, and this is what is called an irrational number. An irrational number and an irrational number is a number that cannot be represented as a fraction of two integers. It's also commonly referred to as phi, and phi is also this symbol right here, and you sometimes see phi as the capital Phi like this. Okay, so we're looking at it. It just looks like just a random number. What's its importance? Have I just made this up? No, I haven't. If you were to Google it, you'll find that I haven't. But let's prove it. So if we have a line, a straight line. I know this isn't straight, but just bear with me. So if we have a line, and if we were to split it into two, such that the larger side titled A, the smaller side titled B, such that these two ratios, so A over B, was equal to this right here. You can do this with any straight line. So such that the ratio was the same as phi, so this was equal to phi. What you will also find, this is the same for any line, if you are able to find this point, that the ratio of A plus B, which you probably seen, is the entire line. So the ratio of that compared to the larger side, so A in this case, is also equal to A over B, which is also equal to phi, which is equal to this number right here. So that's pretty cool. And actually, just want to say something. I'm going to be doing a proof. Literally, that's what I'm doing right now. But this is not a comprehensive proof. There are other proofs out there. If you want a really good proof, if you want to know more about the ins and outs of the golden ratio, I recommend checking out videos from Khan Academy. It'll cover a bunch of topics. They go very in depth. This is just a high level and how it relates to other sequences as well, and real life examples. So yeah, so if you're more interested in it, hope you are, go and check out some of the other material online. So we got this, phi equals A over B, which equals the entire line over A, and that's pretty cool. But let's just prove it, because this right here is the same as A over A plus B over A, just basic mathematics, and we still know that this is equal to A over B, and this is equal to phi. Therefore, we also know that this now equals 1 plus B over A, because when you do A over A, you get 1. Anything over itself except 0 results in 1, and A over B is still equal to phi. And you might notice something, that this number over here, this ratio, is almost the same as this ratio. They're just the inverse. And if we know that phi is equal to A over B, B over A is just the inverse of phi. And you can think of phi on its own the same thing as phi over A, because if you divide anything by 1, you get itself. So B over A, which is the inverse of A over B, is 1 over phi. So what we can do is substitute this in. So phi equals, we'll get rid of this part here because it equals phi. So phi equals 1 plus 1 over phi. And now we have everything in terms of phi or number constants. I just want to do one last thing, or not one last thing, one more thing, and that is to multiply everything by phi. That way we'll get rid of this fraction. So that becomes phi squared, because phi times by phi here is phi squared. So you are timesing it by phi, which is equals to 1 times by phi, which equals phi, and all of this times by phi. And if we're dividing it by phi, it just cancels out and we get plus 1. Let's rearrange it so it's all on one side. Phi squared minus phi minus 1 equals 0. And now you might be thinking, I recognize this. If you don't, how about now? If we substitute phi for x, so x squared minus x minus 1, I bet you're thinking now, you're shouting at your monitor, you're banging it, you're thinking this is a quadratic equation, and you're correct. And we could factor it, but trying to factor this in our head is going to be ridiculous. So we're not going to factor it. We're going to use the quadratic formula, which is minus b plus or minus square root of b squared minus 4ac. I'm not going to show a proof of the quadratic formula or a quadratic equation. Khan Academy plus various other great sources online have those proofs, so feel free to check them out. And if you know your algebra, your quadratic equations, you will know the coefficient in front of this x is the a term. The coefficient in front actually, I'll use a different color. The coefficient in front of this x term is the b term, and the coefficient, or this entire number here, is c. So if you don't have a number in front of it, it's the same thing as multiplying it by 1. So a equals 1, which is right here. And if we were to do b is equal to negative 1, because you also have to use the sign in front of the x squared. It's the same thing as just having a plus. And now let's finally do the c term. So c is equal to negative 1. So now let's start substituting in these values, and we get minus 1 plus or minus b squared, which is minus 1 squared, minus 4 AC, and A is 1, C is negative 1, all of that over 2, 1. Now let's just simplify this a bit. We get 1 plus or minus square root of 1 squared. 1 minus 1 squared is just 1, plus 4. Now let's get rid of the squared. Plus 4, because minus 4 times by 1 is minus 4. Times that by minus 1 is just negating it, which becomes a positive 4. All of that over 2. And simplify that just some more. 1 plus 5 over 2. And this now becomes two different numbers. We get 1 plus square root of 5 over 2, and we get 1 minus square root of 5 over 2. And these numbers are, this one is 1.618, etc., etc. This is the golden ratio, and this one over here is almost the same. This is 0.618, and I have a calculator right here, so I can just quickly check just to make sure I haven't made a mistake somewhere. And I recommend you do it on your end as well. So I'll just check the plus one, let's check the minus, and sorry, this is a negative 0.618. So this is essentially just the negative of this added 1, or if you were to take away 1 from it and negate it. Again, all of this does have a very, very big significance. You can check more about it on the resources online, but for now we're just interested in this. So we've proven that that ratio is equal to the golden ratio. So again, okay, that's pretty cool, that this ratio, and if you were to, if I just keep scrolling up, if you were to just keep splitting this line up, etc., 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 the ratio is still the same of the whole line compared to the larger of the two lines. You still thinking, okay, it's alright, not too bad. I'm sure you've heard of the Fibonacci sequence of numbers. And I'll do the Fibonacci sequence. I'll just write some of the Fibonacci sequence. This is an indefinite sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233, 377. Okay. So just a brief overview, the Fibonacci sequence. Each number is just the previous number, previous two numbers combined. So we get 1. The next number, as there's only 1 there, they reach this 1. This is 1 plus 1. This is 2 plus 1. This is 3 plus 2, 5 plus 3. I think you're getting the picture. So this just keeps on going. What's really interesting is if you get the ratio of one of the numbers, so if you get the ratio of any two of the numbers, so if you, let's say, choose, not any two of the numbers, if you get the ratio of one of the numbers with the previous number, so for the first two sets, it'd be 1 over 1, this equals something. We got 2 over 1, this also equals something. We got 3 over 2. We have 8 over 5. I'm going to skip some. I'm not going to do all of it. And we're going to choose 89 now. So 89 over 55, I believe it was. 55. And now we'll do the largest two, which are these over here. So 377 divided by 233. If we work these out, this equals 1, this equals 2, 1.5. Let me see if I can figure this out in my head. This is something like 1.6. And if I'll do the next one on the calculator. 89 divided by 55 is 1.618. And these two numbers repeat. And if I do 377 divided by 233, we get 1.618025751. The 0.6182571. So that's cool. But if you look at these numbers, they are converging. They are converging to the golden ratio, and if we keep doing this, it gets closer and closer to the golden ratio. So two things that are seemingly unrelated are related in so many ways. But again, you might think, okay, this is just made up. So let's just go into something else. This is something really cool. So if I draw a star out, this isn't to scale. I need to get rid of that line. So if I draw a star, again, this is not to scale. If you have like a proper equal star, what you will find if, and I have not drawn this properly at all because it's going to be hard to show what I'm trying to show here. What you will find is that these two, the ratio of these two, let me use a different color, ratio of these two is the golden ratio. The ratio of this and this is the golden ratio. The ratio of this and this is the golden ratio. So it's appearing in shapes as well. So that's becoming really fascinating now that it's appearing in loads of places. It also appears in the pentagon shape. If we got that is such a bad pentagon. It is ridiculous. It's slightly better. So if we have an equilateral pentagon, if we get any one of its diagonals, and we get the ratio of this, so let's call this A, and we get the ratio of one of its sides, again it's equilateral so it doesn't matter what it is, we have B, this is equal to A over B, and this is equal to the golden ratio. And if we were to assign a value of 1 to B, so we would have A over B, which is, 1, which equals A, and therefore when the length of a pentagon side is 1, the diagonal, any one of its diagonals are phi. So that is really cool as well. But again, you might think, okay, a lot of these shapes are sort of man-made structures, but it goes beyond that. It actually appears in nature, it appears in art, and let me show you some examples. I've got some examples right here. If I scroll up, keep going, got some examples. Here is a example of nature. It appears everywhere. It appears in this example of a solar system in space. It appears in plants, and it's not one of those freaky little coincidences that you just have like a one-off plant that ends up looking like a famous person. It's not like that. That it appears consistently throughout history in nature, and this is an obvious one as well, and it appears here as well. You might be thinking, okay, how does it actually appear there? We've just talked about it in terms of numbers and then lengths of lines, but there's something really, really cool. If you were to draw a rectangle, and if on this line you were to find a point that did bisect it or did split it into the golden ratio, then if you did the same for this rectangle as well, for the smaller rectangle, and then if you did it for this one as well, and let me choose a different color. If you did it for this smaller rectangle, then this even smaller rectangle, and then this one, and then this one. And if you just keep going, obviously I can't really go much smaller than that. You might be noticing that's very similar to the way we did our line, but it's in a rectangle now. So this is the golden rectangular form. And what you might be seeing, hope you are, is that you get sort of a spiral effect. So if we were to draw sort of a line No, I've totally messed that line up. Oopsie daisy, I messed that line up. Oh, see what I did wrong. Oopsie daisy, don't want to do that. So let me just sort of redo this again. So if we were to, it needs to be split this way. Again, that's just my bad. So I'll just quickly do this. So if we split it again, and then if we split it again, and then if we split it again and again. Okay, so if we now were to draw a line, or like a spiral effect, so if we were to join these up, I've just sort of got this in the wrong place. This should be like that. So I've just got the smaller squares in the wrong place. But you sort of see what I mean. You get this spiral effect when you join them up using curved lines. And this appears here, as you can see. You can definitely see it in this one. So the golden ratio is appearing in nature without human intervention, and it has throughout history. If I scroll up some more, I have some examples of art and architecture and photography where it has been used. So it's used by the Greeks. The Greeks were, some people say, overly obsessed with it. This painting that Leonardo da Vinci did is also using the golden ratio heavily, and it is meant to be visually appealing to the eye. Photographers will know of the rule of thirds, and the golden ratio is considered to be a superior system than the rule of thirds when constructing photographs, when placing objects. It's being used in video games. It's being used throughout history in various forms in one way or another. So the golden ratio is this crazy thing that just comes in nature. It's in man-made stuff such as art. It's in shapes. It's in the Fibonacci sequence. It's in a bunch of other mathematical sequences as well. And I definitely recommend that you check it out, Google it some more and find out. So let me just draw. That's probably not the best. I'll do it on here. You can see that this has the same sort of, no, should be the other way around. It has the same, okay, so probably not the best line, ignore that one. This one is a lot better. It has the same effect, so it is an amazing system. Definitely recommend you research it some more. It just fascinated me the first time I came across it. So this is it for the golden ratio. If you have any questions, feel free to reach out. Like I said, there's a bunch of really cool videos online from Khan Academy and other sources covering the proofs of golden ratio in more depth, so feel free to check them out. They cover quadratic equations and other topics that we talked about in this video. And as usual, thank you for watching, and I look forward to seeing you in my next video.